I guess sound check, just in case.
Yeah, we can hear you.
Cool. Okay, I believe we should start. At least this is how it looks like. What are your expressions regarding the lecture? What is your impression regarding the lecture? How do you feel after the lecture?
A bit confused. A bit confused.
Okay, I hope the seminar session will help you to resolve all this confusion. At least I'll try. I'll do my best. Okay, guys. So I want to discuss well, these new notions that were during the lecture. So I want to discuss homomorphisms and isomorphisms. So I want to discuss. So let me like enumerate all the. Let me list all the things that I want to discuss. So the first thing is the homomorphisms and isomorphisms. The second thing is the direct products. And the third thing is the finite abelian groups. So we will discuss finite abelian groups during the whole course because they are frequently used, and we will use them for encryption decryption algorithms. So you'll see them a lot. Okay, but let's start with homomorphisms, just in case. Well, what is a homomorphism? Homomorphism of groups is a map which preserves in a certain way the operation, which means that it doesn't matter whether you take product of elements and then apply the map, or you apply the map and then take the product. This is a homomorphism. And the first question, the first simple question is this: we're given two groups, G and H. How to find all homomorphisms from G to H? Well, we want to find all homomorphisms from G to H. How do we do that? Well, actually, this is an extremely difficult question. This is an extremely non-trivial question. So in general, when we're given arbitrary groups G and H, it's extremely hard to find all homomorphisms from G to H. So that's why we will not do this in general. We will do this in several specific cases when we can solve the problem. So I want to stick to these cases. First of all, it's easy to describe all homomorphisms. So the case number one, it's easy to describe all homomorphisms from the group Z to an arbitrary group H. So let me show you how to produce a homomorphism from Z to H. Let's take an arbitrary element from the group H, just any element you want. Then consider a map which takes an integer k to the element H to the k. So H, we use a multiplicative notation here for the group H. So if you prefer an additive notation, then the map will be k goes to k times H, because raising to a power in additive notation is denoted by multiplying by k. So this is the multiplicative notation, and this is an additive notation. But strictly speaking, this thing is just a different notation for this thing, but they mean exactly the same thing. So this is a map. So this is a well-defined map. What does it mean? It takes any element from Z to an element of H by this specific rule. And there is no problem with this rule. It's defined for all elements, and it gives you precisely one element for each k. So now, it's what I want to say, that this map is always a homomorphism. Indeed, when you take phi of k plus m, this is exactly the same as h to the k plus m, and this is exactly as h to the k times h to the m, and this is a phi of k, phi of m. So this rule preserves the operation. So this is how to produce a homomorphism using an element of H. So when you started from an element of H, you can produce a homomorphism from Z to H. Well, so just in case, are there any questions regarding this? Okay, now, well, it turns out that there are no other homomorphisms. Indeed, if you take an arbitrary homomorphism phi from Z to H, by definition, phi of k, well, let's take an arbitrary element k from Z. Then phi of k is what? Is phi of 1 plus 1 plus 1, etc., k times. Because phi must be a homomorphism, it must take it to the phi of 1 times phi of 1 times etc. times phi of 1, also k times. But this is just phi of 1 to the power of k. So as you can see, if we are given a homomorphism phi from Z to H, each element k goes to an element phi of 1 to the k. So phi of 1 is just your element H. So you just take H to be phi of 1, the image of the generator of Z. Then, so as you can see, this homomorphism coincides with the homomorphism of this kind for the element H given by this formula. So every homomorphism from Z to H is described by an element H. You can take the element 1 to any element of H. And this rule uniquely defines a homomorphism by this formula.
Wait,
For
no,
example,
I don't get it. Could you explain?
Should I repeat something, or is it better to give an example?
Well, maybe an example is better.
Okay, let's do an example. Let's try an example. So suppose that, let's take G to be, your group G is Z, and let's take H to be, well, let's say Z4, okay? And now I want to describe all possible homomorphisms from Z to Z4. What I'm saying is that there is a bijection between Z4 itself and the set of all homomorphisms. And it's given by this rule. If you have an arbitrary element A from Z4, then it uniquely defines some specific homomorphism phi a from Z to Z4. Let me show you how to do this. So so we have like 4 elements here, 0, 1, 2, and 3. Well, the element 0 gives you a map phi 0 from Z to Z4, and it takes k to the kth power of the element 0, which is k times 0. So this is simply a map that taking each element to 0. So the element 0 gives you the homomorphism which takes each element k to the 0 element. Well, is it clear now what's going on? Or should I reformulate this, or just start from the beginning? Or guys, who asked the question?
Okay, so actually, so our initial statement was that any, like the only homomorphism, or wait, like, so we had k from k to h to the power k. That was our initial thing. And we, like, our initial statement was that any homomorphism can be described in this way, or what?
Yeah. So our claim was that every homomorphism from Z to a specific group, let's say Z4, is uniquely defined by an element of Z4. So each element of this group defines a homomorphism from Z to Z4.
Okay, yeah, makes sense.
So now I just list all the elements of Z4, and for each element I produce the corresponding homomorphism. And here I just wrote down the rule how to define this homomorphism. And I use the multiplicative and the additive notation. So for multiplicative notation, if you are given an element h, your homomorphism works by this rule. K goes to h to the k. But if you have an additive notation, the homomorphism works by this rule. Phi h takes k to k times h.
And why are there no other homomorphisms?
Why there are no other homomorphisms? That was, so here was an attempt to explain this. Because if you take an arbitrary homomorphism, well, let's apply this homomorphism to an arbitrary element k. What is k? K is the sum of the element 1, k times. But since phi is a homomorphism, it changed this plus to the operation in the group H. So, so this equality. So this equals to this thing. You just multiply phi of 1 k times. And this is the power of phi of 1, well, phi of 1 to the power of k. So as you can see, if you take an arbitrary homomorphism phi, it takes an arbitrary element k to an element phi of 1 to the k. And phi of 1 is actually your element h from the group H capital. So you see, we represented an arbitrary, so we started from an arbitrary homomorphism and we represented in the form we wanted. Is it clear now?
I don't get why f of 1 is our element from H.
Oh, well, phi is a map from Z to H. If you substitute an element 1 inside phi, it produces an element of H.
Okay, yeah, I see. Yeah, thank you.
Okay, just in case. Okay, who thinks that what's written here is clear? Who understand this? Could you write plus in the chat? I just want to know how many of you think that this is clear what's written here, and my explanation was okay, at least okay. Okay, there are some of you. And also, could you write minus if you still think that something is not okay here, or there was some problems, or I should clarify something? Just don't worry. Okay, now at least I see only pluses here. So let's think that the explanation worked. So now let's go back to this example. So if you want to list all the homomorphisms from Z to Z4, you know that Z4 has 4 elements, so there are only 4 homomorphisms from Z to Z4, and let's write them down. So the first homomorphism, which corresponds to the 0 element, it takes k to k times 0, which is 0, so it takes each element to 0. So you see, mapping everything to the neutral element is always a homomorphism, and this one corresponds to the element 0 here. Now, if we take 1, this homomorphism works like this. You take k to k times 1, which is k. So this is just k modular 4. So you just take each element to, well, modular 4. Well, because our operation here must be modular 4. So this reduction corresponds to the element 1. So when you take 2, then this map phi take k to k times 2 modular 4. So this is third homomorphism corresponding to element 2, and the element 3 corresponds to the map which takes k to k times 3 modular 4. So this is how to describe all possible homomorphisms. So this is how they look like. And by the way, multiplying by 3, since 3 is equal to -1 modular k, this rule is exactly the same as minus k modular 4. This is how to simplify the formula, for example, because 3 is exactly the same as -1 modular 4. You may rewrite this formula using -1 instead of 3. Okay, are there any questions regarding this example? Good. Then let's try to compute something else. Let's try to compute a kernel and the image of one of these homomorphisms. For example, let's take these ones. And we will recall the definition. So we have phi2 from Z to Z4, which takes k to 2k modular 4. What is the kernel of this homomorphism? This is the set of all k from Z such that phi2 of k is equal to 0. And what is the image of phi2 is the set of all elements of the form phi2 of k, where k goes through all elements of Z. So let's try to compute these guys. So what is kernel of phi2? How do you think?
Should be all even numbers, probably.
Yep. This is the set of all even numbers to Z. Why? Because, well, phi2 of k is equal to k, and it's equal to 0 modular 4, if and only if 4 divides 2k. But this is if and only if 2 divides k. So that's why k must be even. So the kernel consists of all even numbers. But what is the image?
0 and 2.
Yep, 0 and 2. So this map is neither injective nor surjective. So the image consists of 2 elements, it's less than 4, and it has kernel. Well, it's obviously must have a kernel because Z is infinite and Z4 is finite, so there is no injective map from infinite set to a finite set. So it must have a kernel, but the image is not the whole set. Now, let's try to do this for Z3, or for phi3, from Z to Z4, when we take k to 3k modular 4. Well, what is the kernel?
All numbers that can be divided by 4.
Yeah. And what is the image?
Three, 2, 1, and 0.
all the remainders. So it's surjective. And now let me show you how to simplify this computation. So you want to go through all numbers like this: 3 times 1, 3 times 2, 3 times 4, 3 times 5, and so on. And the same with the inverses: 3 times 0, 3 times -1, and so on. Yep, because you want to go through all integer k. But you see, and you take them all modular 4. But it's inconvenient to compute with 3. But since you know that 3 is equal to -1 modular 4, you know that this rule is exactly the same as k goes to -k modular 4. So it's more now it's more convenient to compute, because you want to compute -1 times 1, -1 times 2, -1 times 3, etc., -1 times 0, -1 times -1, and so on, and take all of them modular 4. But when you multiply by -1, it's clear that you will get all the elements. So that's why it's clear that the image will be Z4. And now, if you want to compute the kernel, well, one is -k is equal to 0 modular 4, if and only if 4 divides -k. But this is exactly the same as 4 divides k. Well, here it's not, well, for this computation, I mean, for injectivity, well, not for injectivity, for computing the kernel, it's not very important to switch from 3 to -1, but it's just more or less the same. So yeah, so here we can see that the element k is in the kernel if and only if it's divisible by 4. So this is how to compute the kernel of the map. Or you can just do the same computation with this notation: 3k equals 0 modular 4, if and only if 4 divides 3k. But since 3 and 4 are coprime, then 4 must divide k. So this is how it works. Now, are there any questions regarding these examples and how we computed the kernel and the image? Okay, cool. So now I want to discuss the second case when we know how to compute homomorphisms. And this one is the case of a cyclic group. When we're given a cyclic group, let's say Zn with addition, this is a finite cyclic group. So, by the way, can you hear that on the background?
Yep.
You know, there are several kinds of superheroes. There is like a Spider-Man, there is an Iron Man, and here is a neighbor man, a superhero, a new brand superhero. He has drills instead of his hands, and he knows how to make a noise like whenever you want. Yep. Thank you, neighbor man, for being here during our session, seminar session. Yep, he's helping as much as he can. So now I want to describe all possible homomorphism from Zn to an arbitrary group H. Well, it turns out that in this case, we have almost the same description. Well, in order to produce a homomorphism, well, let me use a different notation here. I just want to do that. I want to take an element H, small from H capital, but with an additional restriction. I want this to be a root of unit in the sense that H to the power of n is equal to 1, where n is the same number as we have here, the order of the cyclic group. When we have such an element, we may define a homomorphism from Zn to H by this rule. A remainder k goes to H to the power of k. So when we have this restriction, H to the power of n is equal to 1, we can prove that this map is a homomorphism. Indeed, because here, if I have So you see, the n consists of the remainders 0, 1, 2, etc., and -1. So this rule defines you a map, but you want this map to be a homomorphism. For that, you want to check that if you add two elements, but you add here modular n, your operation is addition modular n. You want this to be exactly the same thing h here as this. But when you compute this, how do you do this? You know that if you add k1 plus k2, it may be larger than n. Then you divide this with remainder. So the result here will be r. So when you compute the left-hand side, you will get h to the power of r. But when you compute the right-hand side, here you will get h to the power of k1 times this thing gives you h to the power of k2. And you want to show that the left-hand side and the right-hand side are the same. So we want to check this property. But here we use the definition of R. It's K1 plus K2 minus Qn. And as you can see, well, in order to get equality here, so here you can rewrite this as h to the power of K1 times h to the power of K2 times h to the power minus Kn. You want this thing to be 1. But in order to ensure that this happens, you pose this additional condition. H to the 1, or h to the n to be 1. And if this happens, then this thing is equal to this thing, so this map becomes a homomorphism. Without this assumption, this map is not a homomorphism. So, okay, let me summarize what has happened here. So for each element h small from h capital with this additional condition, this map defines a homomorphism from Zn to h. And actually, these are all possible homomorphisms. There are no other homomorphisms from Zn to a group H. So who thinks that it was clear? I mean, who's with me? Who understands what happens here?
It's clear.
Okay. So cool. So now, if we want to find if we want to find all homomorphisms from, let's say, from Z4, let me summarize this like this. The set of all homomorphisms from Zn to H is with there is a bijection between the set of all homomorphisms from Zn to H and the set of elements of H of order divisible dividing n. And for each element H, we get this homomorphism phi of H by the rule above. So let's try to use this rule to describe all homomorphisms from Z4 to Z6. So now, well, we have probably less homomorphisms than the elements in Z6, because in order to describe all these homomorphisms, we want to find all elements here. So we want to find all elements here, H from Z6, such that 4 times H equals 0. So that was in a multiplicative notation, and I just rewrote this rule in an additive notation. So we want to find first all the elements satisfying this rule for H equals 0. And then each homomorphism will produce, and for each element of, from this subset, we will produce a homomorphism. So how to describe these, this set? So these are all elements H from the 6 that for H equals 0 modular 6, which means 6 divides for H. but you may cancel 2, and you'll see that 3 must divide 2h. And since 2 and 3 are coprime, this is exactly the same as 3 divides h. So as we can see, the elements satisfying this condition are exactly the elements divisible by 3. And here are 2 elements of this form, 0 and 3. So this set consists of 0 and 3. So there are only 2 homomorphisms from Z4 to Z6. And this is how to write them down. The homomorphism corresponding to 0 will take each element k to k times 0, which is 0. So this is a trivial homomorphism. And the homomorphism corresponding to 3 takes each element k to 3k. And that's it. And that's how it works. Well, modular 6, of course. So these are 2 different homomorphisms, and there are no other homomorphisms from Z4 to Z6. Are there any questions regarding this example?
I have a question.
Yeah.
Why have we decided that there are exactly 2 homomorphisms?
What again?
Why have we decided that there are
Homomorphisms.
exactly 2 of them?
Well, because of the previous claim. So each homomorphism from our cyclic group, which is Z4, and is 4 here, to the group H, which is Z6 here. So all these homomorphisms, they are in one-to-one correspondence with elements of the group H with this condition. So here is this subset in this particular case.
Okay, why do we have this claim?
Oh, but okay, so yeah, well, what I proved that each element gives you a homomorphism, but I didn't prove you in the opposite direction why each homomorphism has this form. Yep.
Yes.
The claim, let me repeat from here. So what's written here shows you that each element with this condition gives you a homomorphism. Okay?
Didn't get it. What does it mean that this element gives me a homomorphism?
Okay, when I given an element H, but did you get the claim for the group Z?
Yes. Yes. So
Here it's exactly the same. So for the group Z, when you are given an arbitrary element from H, you can produce a homomorphism by such a rule. Here, the rule is exactly the same. When you're given an element H, you can use the same rule to produce a homomorphism from Zn. But you cannot use any element H. You need to use an element H with this additional restriction.
But during the lecture, we proved that any element from H, any element from H to the power n is equal to 1.
What again?
Like from Lagrange's theorem, we have a corollary which says that g to the power.
But no. Well, but the Lagrange theorem. Well, the Lagrange. Now you want to apply the Lagrange theorem for the left group or for the right group. You must clarify which group do you use. H could be in any group. And element H small is from the group H, not from the group Zn.
Okay, so if you have a element H small such that H to the power n is equal to 1,
yep,
we can construct
to produce a homomorphism.
Okay, so it implies that we have an arrow from the left to the right, right?
We have
from the right to the left.
To the left, yeah.
Yeah.
And well, actually, and this arrow is actually injective because H is the image of the element 1. So if 2 homomorphism takes the element 1 to different elements, they are distinct. So this is an injective arrow from right to left. And now I want to show that every homomorphism appears from an element H. But this is done in a similar way as it's done for the group Z. If you have a homomorphism, let's say phi, I said phi from Zn to H, then well, let's take k from here. It goes to phi of k. This is exactly the same thing as 1 plus 1 plus 1 k times. So it must be phi of 1 times etc. phi of 1 k times. So it must be phi of 1 to the power of k. So as you can see here, if you have a homomorphism, then the element k must go to phi of 1 to the k. So your element h must be phi of 1. And also, you want to show that you have an additional restriction that kh to the power of n must be 1. Why that happens? Well, because in the left hand side, n is equal to 0. So if you apply phi to the n, this is the same as to apply phi to the 0. But phi to the 0 must go to the neutral element, and phi to the n must go to phi of 1 to the n. So this is h to the n. So this element also satisfies this additional restriction. So this is what, so here I explain two things. The thing number one is this, that if you are given a homomorphism, then it's of the form k goes to h to the power of k. And the second part was that the element h, which is here, also satisfies this additional condition that h to the power of n must be 1 inside the group H. Is it clear now?
No,
Answer the question.
it's not clear.
Okay.
The second part.
What again? The second part is clear or unclear?
The second part isn't clear.
Isn't clear, this one.
No. From the right to the left, it's not clear. Oh, from the left to the right. I don't know. The part in the bottom where we have two brackets. This one is not clear.
So this one is not clear.
Yes, yes.
So what's going on here? I take an arbitrary homomorphism from Zn to H, like any,
Okay.
and I want to show that there is an element H such that this homomorphism is given by this rule.
Okay.
And as an element H, I suggest you to take phi of 1, and this will be your element H. And so, and this sequence of equalities shows you that phi of k is equal to h to the power of k.
Okay, why do we need the second part with n equals 0?
This one,
Yes.
because you see, now I show what did I show you in the first part of this box? I showed you that for this homomorphism, I have found some element h from the group H capital. But here, I want to find an element with this additional restriction. I want this element h to be the root of the power of n. I want it to be identity in the power, rising to the power of n. So I want to prove that this h is not an arbitrary element, but if you rise this element to the power of n, which is the order of the group, you will get the neutral element in H. And this is how you do this.
But n is greater than 0 by default.
Okay, so let me show you how you do this. Well, you actually consider 1 plus 1 plus 1 n times, and you consider phi of this thing. If you add 1 plus 1 plus 1 n times, this is exactly the same as 0. Yep.
Why?
And then it must go to
Why? Yeah, okay.
in the n, because you are
Yeah.
in. But
Okay.
because this is a homomorphism, this must be a product n times, and this is phi of 1 to the n.
Okay, but why do we know that phi of 0 is 1?
Why do we know what phi of
Phi
what,
of 0 is 1.
oh, because phi is a homomorphism, and each homomorphism takes a neutral element to a neutral element.
Yeah.
For Zn, the neutral element is 0 for the group H, which is
Okay.
denote the neutral element by the symbol 1.
Okay.
Okay.
Okay, and what of it? What have we done?
But is it clear now, or should I explain something else?
What is our conclusion?
So our conclusion is this. When you want to describe all homomorphisms from a group Zn to a group H, you find all the elements of the group H with this condition, H to the n is equal to 1, where n is the order of your Zn. And then each element from this set gives you a homomorphism from Zn to H by this rule, which is written here. So this is how to describe all homomorphisms. And this is what I tried to do here.
Okay, yeah, the task, the solution for the task is quite clear. Like we just apply a rule.
Yep, we just applied the rule. Okay, cool. Are there any other questions? Cool. Let's do something else. Let's try something else. By the way, how much? Okay, I have like 40 minutes. I believe this will be enough. Okay, let's go to, well, let's discuss the product. So now the part number 2, the product, direct product. Oh, probably, you know, before going to the part of the direct product, let's find another set of homomorphisms. Let's say you take Z4 with addition, and you take Z5 with multiplication, and you want to find all homomorphism from Z4 to Z5 star with multiplication. How do you do that? First of all, let's describe explicitly Z5 star. This is the set of all remainders co-prime with 5, which is 1, 2, 3, and 4. And the operation is multiplication. Here, the neutral element is this guy. And okay, and now we want to find all elements here such that rising to the 4th power, we will get, so we want to find all elements H from Z5 star such that H to the power of 4 is equal to 1, because 4 is the order of the cyclic group. But as you can see, Z5 star is of order 4. So by the Lagrange theorem, every element satisfies this condition. So this is Z5 star. So we have exactly 4 homomorphisms, because there are 4 elements in Z5 star, from Z4 to Z5 star. So there are 4 homomorphisms. And they are given by all possible elements. So again, from Z4 to Z5 star, well, the first homomorphism takes k to 1 to the k, which is trivial homomorphism, which takes every element k to the neutral element. Then we have k goes to 2 to the k, then k goes to 3 to the k, and the later one, k goes to 4 to the k. Well, all of these are modular 5, because on the right-hand side, we have multiplication modular 5. So these are all possible homomorphisms from Z4 to Z5 star. Are there any questions regarding this example? Cool. Now we're ready to switch to direct product. I believe we can go up. Okay, direct product. Well, when we are given 2 groups, G and H, we can produce the Cartesian product, which consists of all possible pairs. And the operation is the element-wise operation. So when you have G1H1 times G2H2, you will get G1G2 H1H2. Let's say when you have like Z2 times Z3, then how do you, well, your multiplication is usually denoted by addition in this particular case. So how do you add these two things? You just add A and C modular 2, and you add B and D modular 3. So this is how your operation works in this particular case. Just in case, the neutral element here is the product of neutral elements, which is 0, 0, and an inverse element for AB is minus A minus B. Well, where minus A, well, you know how to compute this. It's 2 minus A if A is non-zero, or just A if A is 0. So this is how to compute inside the direct product. But what is interesting is how to compute an order of an element in a direct product. So let's do this. But before going to the next task, are there any questions regarding the definition? Just in case. I believe the definition should be clear. So let's try to compute an order of an element. So suppose we have this direct product of groups, and we have an element here, which is a pair of elements. And we want to compute its order. But what are we given? We know the order of the element G, and we know the order of the element H in the group G and in the group H. So how do you compute the order of this pair when you know the order of the group of G and H? Okay, well, you want to raise this element to the power of k, and let's see when we get the neutral element. And we want to find the smallest possible positive integer k with this property. But first of all, let's describe all integer k satisfying this property. Well, this happens if and, well, the left hand, we may compute the left hand side. By the definition, the left hand side is g to the k, h to the k. So this equality holds if and only if g to the k is equal to 1 in the group G, and h to the k is equal to 1 in the group H. But the first condition holds if and only if the order of G divides k. And the second condition holds if and only if the order of H divides k. But when we, this happens if and only if the least common multiple of these orders divides k. LCM of the order of G and the order of H divides k. So when we're seeking for the least possible positive k with this property, we should take the least common multiple. So this will be the order of the pair GH. So when you want to compute an order of an element in a direct product, you just take the least common multiple of orders of its coordinates. Are there any questions regarding this? Okay, then let's try to compute the orders of elements in a group like this, Z2 times Z3. So there are 6 elements. I'm going to write them all down, and could you tell me the orders of these elements? So these are the elements. So what is the, and so let me write down the elements here. The elements here are 0 and 1. The elements here are 0, 1, and 2. What is the order of 0?
Infinity.
No. The order of 0 is 1.
1.
Because if you raise it to the first power, you already get 0 when you multiply it
But
by
the
1.
neutral element is 1.
What again?
The neutral element is 1.
No, the neutral element is 0.
Why?
Because the operation here is additive.
Okay.
When you write Z2, Z3, you will always use plus modular 2 and modular 3. If you use multiplication, this is not a group because 0 is not invertible. You cannot divide by 0. There is no element such that 0 times something gives you 1 modulo 2.
Okay.
So yeah, so neutral element here is 0, and here is also 0. So 0 has the order 1, and the element 1 has order 2. Why? Because 1 plus 1 equals 0. So you, this is the smallest possible thing you need to take. And what are the orders here? 1, 3, and 3. Are there any questions regarding this blue computation on the left?
No questions.
Okay. So now could you tell me the orders of these elements?
1, 3, 3,
1,
2, 6, and 6.
1 or 2?
2,
2.
2.
6, and 6.
Okay. Yeah, that's right. That's right. So that's how you compute the orders of the elements in a direct product. Are there any questions regarding this? Cool. Well, now I want to go to the Chinese remainder theorem, and I want to play with it a little bit, because this is one of the more important tools in this area. So what is the Chinese remainder theorem? So we have these cyclic group, and we may form a product of these two cyclic groups. Well, in general, you will always have a map from the left-hand side to the right-hand side, which takes an element k to k modular m, comma k modular n. And this map is always a homomorphism. This is a homomorphism. Well, if m and n are not coprime, this is not an inject. This one is neither injective nor surjective. But if m and n are coprime, then this phi is an isomorphism. That was the Chinese remainder theorem. So if you have this additional condition, this is an isomorphism. And let's write this isomorphism down in a specific case of Z2 and Z3. So in this case, we have Z6 and Z2 times Z3, and each element K goes to K modular 2, K modular 3. Well, but since this map is an isomorphism, there must be an inverse map. For example, if you are given a pair of elements here, A and B, where A is a remainder modular 2 and B is a remainder modular 3, then there must be a rule which takes this pair back to a remainder modular 6. So I want to discuss how to find this rule. Of course, in this particular case, you may list all the elements on the left. So you may use just brute force. Let's write all the elements on the left. 0, 1, 2, 3, 4, 5. These are all the elements. And let's compute their images. Well,
0, 0. 1, 1.
0, 2. Then this is
1, 0.
0. 0, 1. And 5 goes to 1, 2. So now, since you know the list, you see, you have the list of all elements on the left and the list of all elements on the right. So now you just, you can tell that, okay, if you're given 1, 0, it must go to 3. If you're given 1, 1, it must go to 1. If you are given 1, 2, it goes to 5. Well, because of, so here, since you can list all the elements, so you can reverse the map. But this is not interesting. I want to write a formula for the inverse map. So I want to find a formula. So let me show you how to do this. And I want to do this in a general, in the general case. And then I will demonstrate you this formula in this particular case. So first of all, what I want to do, I want to find an element S which goes to 1, 0. And then I want to find an element T which goes to 0, 1. If I find such elements S and T, this simply means that the inverse map must take 1, 0 to S and 0, 1 to T. But then, if I am given an element AB, this means that well, this is exactly the same as A0 plus 0B, but this thing is 1, 0 plus etc. 1, 0 8 times. And this thing is 0, 1 plus etc. plus 0B, plus 0, 1 B times. So when you apply the inverse homomorphism, isomorphism, let's say it's psi. So when you apply psi to AB, this is the same as to apply psi to this thing. But here, since psi is a homomorphism, it takes the operation to the operation. This is the same as psi of 0, 1 plus etc. psi of 1, 0 8 times, plus psi of 0, 1 plus etc. plus psi of 0, 1 B times. But you see, psi takes 1, 0 to S and 0, 1 to T. So here it's written S plus S plus S 8 times plus T plus T plus T B times. So this is AS plus BT. So as you can see, this element must go to this one. So if we know these elements S and T, so the formula in the opposite direction is given by the rule. I want to write it down here. AB goes to AS plus BT. So you multiply A by this specific element, multiply B by this element, then you sum the result, take the result modular M times N. So here you also need to take the result modular M times N. And this is how the inverse map works. Just in case, who with me? Who's with me here? Who understands what's going on here?
It's clear.
Yeah.
Okay, are there any questions? Okay, so now the only thing which is missing is how to find these elements. Again, if you can list or casually find such element, that's okay, but I just want to find a rule how to do this like algorithmically. And there is a way to find such elements. Well, here is a rule. When you're given two coprime integers, you must remember that you can always express the GCD, which is 1 here, as a linear combination of the initial integers, which is um plus vn, where u and v are some integers. You can always find u and v such that the GCD has this form. Okay, now let's take this part and move it to the right-hand side. You will get 1 minus um is equal to vn. And I want to denote this number by s. And now, as you can see, s is equal to 1 modular m because of this part. And s is equal to 0 modular n because of this part. And as you can see, we have found the element s with the required property. It gives you 1 modular m and gives you 0 modular n. And if you take this part and move it to the right, you will get 1 minus Vn equals um, which is t, and then t gives you 0 modular m, and t gives you 1 modular n. So because of, come on, because of this, and here because of this. So this is how to find, in general case, these two elements s and t. And when you, so in order to find these elements s and t, you need to find this representation, and there is like extended Euclidean algorithm to find such a representation, and the extended Euclidean algorithm gives you u and v, and then you just use these expressions, for example, these and these, to get s and t. And then when you have this s and t, you write down this formula for the inverse map. Just in case, are there any questions regarding this?
No.
Okay, so let's go back to our example with the 6. So in this case, as you can see, s is equal to 3 and t is equal to 4. Well, here we know this because we have this list. So the inverse map is given by 3a plus 4b modular 6. So this is how you get the inverse map. Okay. And if you want to use this rule with with the GCD, so let's see. You just what do we do? You just take 3 minus 1 times 2 equals 1. So this is how you write down the expression of the GCD using 3 and 2. And if you move these element on the right, you'll get 3, which is this expression. And if you move 3 on the right, you see what you will get. You will get minus 2 equals minus 2. So the rule from below suggests that you have to take the element minus 2 instead of t, which is t prime. But minus 2 is equal to 4 modular 6. So it doesn't matter which element you use. So I just wanted to show you that the rule below may give you a negative integer, but it doesn't matter. You may just replace this negative integer by a positive integer modular 6, or you may use this minus 2 here in this formula, because at the end you will do this modular 6 operation here, so the result will be correctly defined remainder modular 6. So it doesn't matter. You may use 4 or minus 2, the result will be exactly the same. Okay, so this is how to find the inverse map. Now let me discuss the other piece of the puzzle. I want to discuss this classification result from the end of the lecture. And I want to discuss how to find all possible finite abelian groups of a specific order. So, well, as you can see, we may have these 6, and oh yeah, by the way, finite abelian groups. Finite abelian groups. Yeah, such a nice acronym. So there were several claims without proof. The claim number 1 says that if you have a finite abelian group, then it always isomorphic to a direct product of cyclic groups. So every finite abelian group can be represented in this form. So, and as I mentioned, for example, Z8 star can be represented as Z2 times Z2. If you take Z5 star, it can be represented as Z4. So even if a group initially has a very strange form like here, you still may find an isomorphism to a direct product of cyclic subgroups. So this simply means that the left-hand side and the right-hand side, they are exactly the same groups. And if you want to study the properties of this group, this is the same as to study the properties of this group. Or the same happens here. For example, if you want to find all elements of specific order in this group, it's sufficient to find all elements of this specific order here and then translate these elements to the left-hand side via your isomorphism. So it's probably hard to produce an isomorphism, but you usually need to produce it once. And then when you have this isomorphism, you can move the elements from the left to the right and vice versa. And some problems are easier to solve using this representation, and some problems are easier to solve using this representation. So this is the idea of an isomorphism. So even if a group looks like something different, you can always represent it in this form. That's first important claim about finite abelian groups. And usually when you deal with finite abelian groups, they are already given in this specific form or in this, and you just want to recompute them somehow in a more convenient way. So let's drop the problem of how to recompute each group in such a form and deal with this form explicitly. So what kind of problems we would like to solve? Well, first of all, we want to know when two groups are the same. For example, when we may have Z6 or Z2 times Z3. So they look like differently, but because of the Chinese remainder theorem, they're the same. But what happens with Z4 and Z2 times Z2? They are not isomorphic. Well, I was trying to explain it during the lecture, but since I didn't have enough time, I was very quick. So let me repeat the argument. So suppose that they are isomorphic. If they are isomorphic, then, well, this is basically the same group, but represented in a different form. But if this is the same group, then the number of elements of a specific order must be the same. So if you compute the number of elements from Z4 of order 4, this number must be exactly the same as the number of elements of order 4 from this product. Why? Because, well, if you are given an element of order 4 here, you may apply this isomorphism. It goes to some element here, and this element must be of order 4. And vice versa. If you have an element of order 4 here, you apply the opposite isomorphism, and it goes to an element of order 4 here. The isomorphism preserves the order of elements. So that's why these two sets must have exactly the same amount of elements. But how many elements of order 4 are here? Who can tell me?
1.
Which one?
I don't. Excuse me. Yeah, it's 0.
0. There are no elements of order 4. Why? Because if you multiply each element by 2, you will get to A to B, which is 0. So each element is, well, when you take an arbitrary element and raise it to the second power, you will get the neutral element, because multiplying by 2 in the additive notation is the raising to the second power. So the second power of each element is already the neutral element. So that's why there are no elements of order larger than 2. So the right-hand side is 0. But how many elements of order 4 are on the left-hand side?
2.
Yep, exactly. And
1 and 3.
Yeah, 1 and 3. Yep. So as you can see, this is impossible. So this contradicts to the fact that these two groups are isomorphic. So if you want to check that two groups are not isomorphic, you need to find a property which holds under isomorphism. For example, this is an example of such a property, the number of elements with specific order. So if you have different number of elements of specific order for the left and the right hand side, then the left and the right hand side are not isomorphic. This is how to prove this directly. But, well, this is very tedious. And people used to use some simple and easy to use criteria. So I want to show you two simple to use criteria. The criterion number one is this. You want, so when you're given some cyclic group, you want to apply the Chinese remainder theorem and rewrite this group in a specific form such that this form is unique. So when you want to compare two different groups, you just rewrite each group in this specific form, and then you just compare these two forms. If these specific forms are exactly the same, then the group were isomorphic. If these specific forms are different, then the groups were not isomorphic. And there are two different specific forms. Specific form number one is this. You want to rewrite your group as a product of cyclic subgroups such that the order of each subgroup divides the order of the next one. This is the form number one. It's okay. And the form number two, you write your group as a product of cyclic subgroups, where the order of cyclic subgroup is the power of a prime number. The prime number may go with repetition. These guys are prime, and they may go with repetition. And this form is unique up to change the order of factors. For example, you may write Z2 times Z3 or Z3 times Z2. It doesn't matter. So let me demonstrate how to use this thing on a specific example. For example, let's take these two groups, Z10 times Z3 and Z5 times Z6. Well, they look different, but are they really different? Let's check. Well, first of all, is the first group written in the first or the second form? Tell me. Is it presented in the first form?
No.
No, because 3
Nine.
doesn't divide 10 and 10 doesn't divide 3. So it's not in the first form. So it's not a specific form. But it's also not the second form, because 10 is not a power of prime number. The same happens here. 5 doesn't divide 6, 6 doesn't divide 5, and 6 is not a power of prime. So they are not presented in the first or the second form. So let's rewrite them in the second form. It's easier to rewrite first every group in the second form. So how do you do this? You find each multiple which is not a power of a prime number. For example, here it's 10. 10 is a product of 2 and 5. So using Chinese remainder theorem, this guy is just a product of 5 and Z5 and Z2. So the whole group is isomorphic to Z5, Z2 times Z3. Well, I will, so, and how do you write this isomorphism? So for example, if you have an isomorphism between Z10 and Z, let's do it in different way. So here, each element is presented in the form A, B, where A is from Z10 and B is from Z3. And when you go down, you go by this rule. So you just apply for this guy the isomorphism from the Chinese remainder theorem in the direct way. You may also write down the isomorphism in the opposite way, like this. But here you need to find this rule for the inverse map from the Chinese remainder theorem. But in any case, so this is how you apply. So this is how you find the isomorphism. So if this guy is isomorphic to this guy, then the whole product is isomorphic to the whole product. And on the level of elements, this is what happens. So when you go from up to bottom, you apply this. When you go from bottom to up, you apply the map, which here coincides with the reverse map from the Chinese remainder theorem. So on the right-hand side, you do the same thing. So this 6 is represented as Z2 times Z3. And also we have this Z5 here. So these two groups are also isomorphic. And now, as we can see, each cyclic factor here and here is just a power of prime number. Well, I mean, the order of the cyclic factor. So now this is the second form. And this is the second form. And the second form is unique up to changing the order of factors. But here, well, it turns out that I wrote everything in exactly the same order. So I don't even need to change the order of factors. As you can see, the left-hand side and the right-hand side, they look exactly the same. So here it's just the identity map, which is an isomorphism. So here we have isomorphism and here we have isomorphism. So these two groups are isomorphic. And when you need to produce a specific isomorphism, you do this. When you want to write down the isomorphism from the left to right, you go down, then you go right, and then you go up. And you compose all the maps. When you go down from this guy to this guy, you apply this direct isomorphism from the Chinese remainder theorem. When you go from left hand side, when you go right, well, you probably just change the order of the letters, but here the order is exactly the same. And then you go up from here to here, applying the reverse isomorphism from the Chinese remainder theorem from here to here. And here we even know how to do this. Let's write it down. So when you go here from up to bottom, xy goes to xyy, and when you go from bottom to up, let's say zw goes to what? Here it's x, and here we know that it's, what was that? 3z plus 4w, because that's an isomorphism for z2 times z3 with z6. So when we go from left to right, what do? We take A and B. When we go down, it goes to A, B. Now, when we go right, well, we do nothing, because the order of the factors is exactly the same. And when we go up, we apply this map. So A here, and here we have 3A plus 4B. So this is the formula for the isomorphism from the left-hand side to the right-hand side. So this is how to produce the formula for this isomorphism explicitly. And if you want to produce the inverse isomorphism from right to left, you go down here, you go left here, and you go up here. So you do exactly the same thing. And in order to complete the formula, you need to find the formula here for the reverse isomorphism for this isomorphism from the Chinese remainder theorem. But you do this in exactly the same manner. So do you have any questions regarding this computation? Okay, but if we have something like this, let's say we have z, let's say 4 times z6, and something Z2 times Z12. Well, the right-hand side is represented in the first form, but the left-hand side is not represented in the first form. So let's represent them both in the second form. So here it's Z4 times Z2 times Z3, and here is Z2 times, and 12 is 4 times 3, so it's Z4. Oh my God, I did it wrong. It's also isomorphic. I wanted to produce an example which gives you a different thing, but yeah, here it's also isomorphic because you see we have exactly the same thing here, and here. Let's do it one more time. Which one should I use? Something like Z6 times Z10 times Z10 Z60 times Z10. Well, when we want to compare these two groups, well, just decompose the first one as Z2 times Z3. The second one is Z2 times Z5, and then again Z2 times Z5. And for the second part, we have Z2 times Z5 for the second factor, and 60 is something like 3, 5, and 4. So Z3 times Z5 times Z4. This is how it works. And now when we look through all the factors, let me underline the common factor. And as you can see, here is the difference. On the left-hand side, we have Z2 plus Z2. On the right-hand side, we have Z4. So these representations are different, so they're distinct. So these two groups are not isomorphic. Okay, so is it clear? Should I explain something else? Okay.
Yeah, I have one question.
Yeah, okay.
Why can't we divide Z4 into Z2 and Z2? We're allowed to. Well,
no. The Chinese remainder theorem works only when M and N are coprime. So for Z2, it doesn't work because the GCD of 2 and 2 is 2. So they are not isomorphic by the Chinese remainder theorem. But that's not an argument. The right argument is to show directly the reason why they are not isomorphic. And we have already shown before, like here. Let me go back. I have already explained that Z4 is not isomorphic to Z2 plus times Z2.
Mm-hmm.
But here it's not enough to use this fact. Well, actually, what's going on here? Well, it may happen that these two groups are not isomorphic, but after multiplying them by some other group, they become isomorphic. But this will never happen. Well, almost never happen. Well, it may happen, but in this case, it doesn't happen. So in order to check this, you just well, if you multiply by the same group, it will never happen that they become isomorphic. But if you multiply them by different group, for example, you may multiply the left-hand side by Z2 times Z2, and the right-hand side by Z4, they become isomorphic. But if you multiply them by the same thing, they will never become isomorphic. Well, this is something that you have to prove, but I'm skipping all these things without proof because it's more important to know how to use things rather than how to prove them. So what I'm trying to explain how to use things and how to deal with them. So here, if you want to compare two groups, you just stick to the second or the first presentation of your group and just compare these specific presentations. Okay, as I can see, I have -3 minutes. Don't you mind if I discuss one additional problem? I mean, do you have time for that and desire or not?
Yeah.
Okay.
Well, actually, not really. don't understand the last thing, like how we.
Oh, there is a
Okay.
question. So what should I
Yeah, right.
explain? Just tell me. The later one.
So like the entire principle, like kind of didn't really. So what are we what are we trying to do?
Okay. So suppose we're given finite abelian groups which are given in this form, like direct product of cyclic groups. Like the first group is Z10 times Z3, and the second group is Z5 times Z6. Now, there is a question. Are they isomorphic? Are they the same or not? So this is the question we want to address. So I want to understand how to check this. So there are two questions. How to check if they are isomorphic or not. And the second question, if they are isomorphic, how to produce an explicit formula for the isomorphism between them. So here, I wanted to explain both questions. So the question number one is answered by this problem. So this is how you solve the problem of whether they isomorphic or not. So you take the first group and reduce it to a specific form, for example, to this form. And you take the second group and reduce it to a specific, to the same form, the second form. And how do you reduce? You reduce this using the Chinese remainder theorem. And then you just compare these forms. If they are the same, then the initial groups were isomorphic. If they are different, then the initial groups were not isomorphic. And here was an example. So when you take Z10 times Z3, you apply the Chinese remainder theorem for this factor, and you get Z5 times Z2, and then times Z3, the remaining Z3. And if you apply here the Chinese remainder theorem to the Z6, you reduce this thing to Z5, Z2, Z3. And now this is the specific form of this kind, and this is the specific form of this kind. And as you can see, these two forms are exactly the same. So this means that these two groups were isomorphic. So this is how to check if they're isomorphic or not. Well, is it clear now? Or still there are some problems?
Okay, I get the idea, but like all these A, like U and V, like what were we doing? Like
okay. So now, well, when I say that I reduce this group to this one, exactly this means that when I apply a Chinese remainder theorem to this factor, then the whole group is isomorphic to the whole group here. And what does it mean that they are isomorphic? It means that I can produce a map from this group to this group such that this map is a bijection and it preserves the operation. And if I want to produce a map, I can write down the map using elements. So what is a map from this guy to this guy is a rule which takes an element here. What is an element here? It's a pair, A and B, where A is from Z10 and B is from Z3. And if I want to produce an element from the bottom group, I need to produce a triple. So how do I produce a triple here from a tuple here? I just apply the isomorphism from the Chinese remainder theorem to this element because it lies here, and it goes to a pair of elements from here, and I apply the identity map to the third factor, which means that B goes here. So this is just the explicit formula for the isomorphism from up to bottom. And the left-hand side of this isomorphism, which is this part, is taken from the Chinese remainder theorem because I applied the Chinese remainder theorem to this part. Is it better now?
Yep.
So, and if you want to go in the opposite way, because if you have an isomorphism, you have an inverse map for this isomorphism. So then you need to apply for these two guys, U and V, they live here, you need to apply the inverse map from the Chinese remainder theorem. So in order to find this map, well, you need to do some computation with 5 and 2, and then you will find a formula for the map in the opposite direction. But I didn't spend my time to write the explicit formula here. And exactly the same thing happens here. So when you go from up to bottom, this is how the map works. So y lives here, so it splits into a pair of y's. And so I skip all these modular 5, modular 2, modular 3 things because, well, you know, it's just a noise in the formulas. But, well, definitely you need to write here y modular 2, y modular 3. And if you go in the opposite direction, we already know the formula because we computed the opposite map for z6. It takes z and w to 3z plus 4w. So this is how it works here. And now, if you want to compute the isomorphism between these guys explicitly, you see what you're doing. You go with the isomorphism to the bottom. Then the bottom part coincides with the bottom part on the right-hand side. Well, probably you need to do some permutations, but here you see the blue is the 5 is first here, the 5 is first here, the second is second here, the 2 is second here, the 3 is third here, the 3 is third here. So the map from left to right just takes element A, B, C to element A, B, C. So you don't need to do anything. So when you go from up to bottom, from left to right, and from bottom to up, you go through 3 isomorphisms, and composition of isomorphisms is also an isomorphism because it's a bijection preserving an operation. So this gives you an explicit formula for an isomorphism from the left-hand side to the right-hand side. And here I tried to write this composition explicitly. So I took a pair AB, go down, then go right, and then go up, using all the formulas that are written here. And this is the precise formula for the isomorphism from the left to the right. Igor, is it okay now?
Yes, thank you. Yeah.
Yeah, by the way, if I explain something and it becomes already clear and you want to stop me, just don't hesitate to tell me, because I mean, I don't know how much details should I provide, so I try to go through all the details. So it's not, if it's enough, just don't waste your time.
No, it was just enough details, yeah.
Okay, so that's good. So, and here was an example where you can check that 2 groups were not isomorphic. So you just reduce each group to the second unique representation, and the red part is common one, and the blue part is different. So since we have different representations, then these 2 groups are not isomorphic. So this is how it's solved. Okay, are there any other questions regarding this? Okay, then if you don't mind, I just want to discuss one additional problem, and I promise that's the last problem I want to discuss. I just want to compute the number of finite abelian groups of specific order. So it's a simple corollary of this uniqueness result, but I believe it should be discussed explicitly. So suppose I want to compute the amount of finite abelian groups of order 8. G is finite abelian group. So how to find all finite abelian groups of order 8? Well, you see, by the classification theorem, we know that our finite abelian group must be of this form. Well, let's reduce this finite abelian group to the second form. But its order, if we compute using this presentation, is just a product of these numbers. And it must be 8. So as you can see, so the only options for these cyclic subgroups is the cyclic subgroup of order of power of 2. So the options we have is Z2, Z4, and Z8. And now, having these blocks, we want to produce a group of order 8. So there are 3 options. You may take Z2 times Z2 times Z2, or you may take Z2 times Z4, or you may take Z8. So these are all possible groups of order 8 well, all possible finite abelian groups of order 8. So there are only 3 finite abelian groups of order 8, and this is the complete list of all these groups. Are there any questions regarding this?
Why it is all possible combinations?
Because, well, okay, so you see, if you have a group, finite abelian group of order 8, it must be represented in this form. But when it's represented in this form, its order must be this number, and this number must be 8. So these powers, so these PIs must be powers of, well, must be 2. So each PI is a 2, and the difference is how do we choose these powers, K1, K2, etc. So these are all options for the factors that we may encounter in the group G. So the only thing that may happen is how to combine these groups together using product in order to get the group of order 8. And these are all possible ways.
Okay.
I mean, what was that really enough? I mean, is it clear?
Yes, yes.
Okay, good. And let me give you the second case is when the order of G is the wrong color. The order of G is 36, which is 2 to the 2, 3 to the 2. So here, the order of the group is not a power of prime. It's a product of primes. So then what you do, again, so your group must be in the form like this. So its order will be the product of these primes, and it must be 2 to the 2 times 3 to the 2. So the options for these guys are as follows. So you may have Z2, you may have Z4, you may have Z3, or you may have Z9. And now you want to multiply them in such a way to get a group of order 36. It means that, well, for the prime 2, you need to get, well, a product of 4 elements, and for the prime 3, you need to get a group of 9 elements. So you have the following options: Z2 times Z2 or Z4. And here you have Z3 times Z3 or Z9. And now you may multiply each element from the right with each element on the left. So you may multiply these two, you may multiply these two, you may multiply these two, or you may multiply these two. So you will get 4 groups. The first option will be Z2 times Z2 times Z3 times Z3. The second option will be Z2 times Z2 times Z9. The third option will be Z4 times Z3 times Z3. And the fourth option will be Z4 times Z9. And these are all possible finite abelian groups of order 36. So in general, what would you do? You find a decomposition for the order of the group into the product of powers of primes. Then for each prime, you find all possible cyclic groups. So they're just Z, for example, if you have Z to the power of K, then you may have Z2, Z4, Z8, etc. to Z to the 2 to the power of K, and so on. And then you just combine these groups together to get exactly this amount of elements. So this is what we did here. So we have 2 to the 2, which is 4. So we get all options to get 4 elements here. For this part, we get all options to get 9 elements here. And then you just multiply the results for 2 and the results for 3. And you will get all options where you have 4 times 9 elements.
Why can I take the 6 by the 6?
Well, first of all, you may take the 6 times the 6, but you will get this group. So this approach guarantees that you get exactly this, you will get all the groups and you will list each of them just once. So you will get a list without repetitions. And why you don't get this 6? Because 6 is not a power of a prime number. So here you want the blocks to be the powers of prime numbers. You see? All these guys are just powers of 2 or 3.
Okay, but 9 isn't a prime number.
It's a power of prime. It's 3 to the power of 2, and 4 is a 2 to the power of 2. You see here, P1 to the K 1 is just a power of prime.
Oh, okay.
9 is 3 times 3. It's a second power of 3. So if you use just powers of prime numbers as building blocks, you will get all possible groups, and you list each group once. You will get the list of groups without repetition. So here, as you can see, you get exactly 5 groups. Just in case, are there any questions regarding these algorithms?
Do we have to prove that they're exactly like group? Because, okay, ignore it.
Okay.
No. Like we had an example, Z4 and Z2 by Z2.
Okay.
So, and we have proved that they're not isomorphic. So
Yep.
should we do it in this case?
Oh, but in this case, it follows from this general result. Let me go back. So from this result, because you see, we produced the groups in the second form. Each product is a power. Well, the order of each product is the power of prime number, and all 4 options have different have different form. They all have different form. You see, for example, when you compare this one with this one, they're different here. Z9 and Z3, Z3. This guy and this guy, they're different here. This guy and the later one, they're different everywhere, like here and here and here and here. Because these are 4 completely different representations in the second form. They are all not isomorphic. So here you don't need to prove this, you just cite the results. So since this is given in the second form, so you don't have to, so it follows automatically from the theorem.
So you mean that it follows from the algorithm itself?
Yeah, because by the algorithm, we just produced the list in such a way that we have no repetition. Yep, exactly.
Okay, but probably the 3 by the 3 is isomorphic to that 9.
No, it's not. First of all, it's not. Well, again, do you believe in the theorem that was above?
Which theorem?
Okay. Okay. Let me. Oh, I'm sorry. I did something wrong. Let me reformulate this theorem here once again.
We can say that 9 have order 9, 1 has order 9, and in the presentation that 3 by Z3, there is no number with order 9.
Yeah, that's exactly how you would prove this explicitly. So the 3 times Z3 is not isomorphic to Z9 because Z9 has elements of order 9, and Z3 times Z3 doesn't have elements of order 9. This is exactly how we did this for Z2 times Z2 and Z4. But you don't need to use this because we have this thing that if you have 2 groups of this form, and they are isomorphic if and only if, up to changing the order of factors, P, well, first of all, the M must be equal to R, so there must have exactly the same amount of factors. Then Pi must coincide with Qi, probably after applying the permutation, and the powers Ki must coincide with Si. So this is the uniqueness result. So that was formulated above. So this is how we compare the groups using our algorithm to compare finite abelian groups. So in this form, they are presented uniquely. So since this form and this form, they are different, so they are automatically not isomorphic. So it requires a proof, but if you believe in the result, saying that if this happens, they are different. They are not isomorphic. Then just use the result. Kirill, is it okay or still?
Okay.
Okay, guys, I see that I spent a lot of your time, but I believe since you're here, it's probably not that bad. But still, do you have any questions? Are there any questions?
Yes, I have a lot of questions.
Okay, let's go.
Okay, firstly, with our property about the number of homomorphisms. Okay, I didn't get the proof. Why do we so?
Which one? This one? Oh, there was
1 minute. Okay, I didn't get the idea. So
this one.
This
you
one,
mean.
yeah.
But before going there, did you get the idea for this guy? How did we get the case number 1 where we have homomorphism from Z to H? Because these are completely similar.
I don't remember it.
Okay, so let's go. So what happens here? When we describe homomorphisms from Z to H, first of all, for each element H.
What is H?
What is, H is an arbitrary group. Z is the group of integers with addition, and H is just any group. The group of matrices with respect to addition, or GLN with respect to multiplication, like Z8 star with multiplication, or like anything. And now you want to compute all homomorphisms from Z to this group H. Well, it happens that in this case, it doesn't matter what kind of group H you are given, you know how to compute all possible homomorphisms from Z to H, like everything. So how do you do this? Well, in order to describe all possible homomorphisms, I need to do 2 things. The thing number 1, I need to present you a construction for a specific homomorphism. That's the first thing. And the second thing, I need to prove that this construction describes all possible homomorphisms and you don't have any other homomorphisms. Well, is it clear on this level?
More or less.
What is confusing you?
Let's continue. I will ask you if something.
Okay, so let's go through this thing. So first of all, a construction. So when you want to produce a homomorphism, well, you need to start from something. You need some data, because how do you produce a homomorphism? Like you need something. So as this something, I suggest to use the element H. Just take arbitrary element from the group H, like any. And then using this element H, I can produce a homomorphism, which is this. And the homomorphism is given by this formula. K goes to H to the K. And here is the proof that this rule is actually a homomorphism. So this gives you a homomorphism for each particular element of the group H capital. Just fix an element, this gives you a homomorphism. Fix a different element, this gives you a different homomorphism. How does this homomorphism work? This is how it works. Is it okay?
No, I don't understand.
Okay, let's.
What are requirements? What are requirements for a homomorphism?
Okay, let's write it here. I just want to start from the scratch. I believe it will be better. So we want to find all maps. So what are we given? We are given H, an arbitrary group. Then we have a group, the group Z with addition. Well, I will denote multiplication in the group H by the dot. So now we want to find all maps from Z to H such that phi of k plus m equals phi of k times phi of m. This is the requirement for the phi being homomorphism.
Okay.
Okay, so, and we want to find all these maps. You may do it using brute force, like just describe all possible maps and then check which of them satisfy this property. But this is a nightmare. Instead, I suggest an explicit procedure. First of all, examples. I want to produce some homomorphisms. So I want to produce a construction. So construction suggests take an element H from H capital. Then for each element H from H capital, I can produce a well-defined homomorphism. And this homomorphism works like this. It takes integer k and it takes this integer k to H to the k. So this is how you produce a homomorphism using an element H from H capital. So first of all, this is a map, and this map is a homomorphism, so it satisfies the rule above. Okay? So now I listed you some homomorphisms. Well, actually, there is one step I missed. So if we have different elements, then these homomorphisms are different. Well, indeed, what does it mean the homomorphisms are different? Well, it means that we're given different maps. How do we compare maps? Maps are different if they take some element to different element.
Okay.
For example, if you apply both homomorphisms to the element 1, then by definition this goes to H and this goes to H prime. And if H and H prime are distinct, then these guys are also distinct. So this is the place where these two maps are different. So different elements gives you different homomorphisms.
Okay.
And now I want to prove that there are no other homomorphisms. So if you are given a homomorphism from Z to H, then there exists an element H such that phi coincides with one of the homomorphisms above. Now, how to find? Well,
is it our statement or what is it?
Yeah, this is a statement. I claim that every homomorph, well, the statement has this structure. This is what we're given, and this is what we want to prove. So from A, so A implies B. The structure of each statement has this form, and this is exactly what's written here. So every homomorphism, so I should write here homomorphisms. So every homomorphism for phi for Z to H, for every homomorphism from phi from Z to H, there exists an element H small from H capital, such that phi coincides with phi H from the construction above.
Okay.
So, and then if we prove this, it simply means that all the homomorphisms have this form phi of H. Okay?
Okay.
Well, now I can just tell you this element explicitly. Well, just let's define H to be phi of 1.
Why?
That's a different question, but let's try this approach. Just like, you know, when you dream and during the dream, the God came to you and told you, you know, take phi of 1 as the element H here. You just wake up and try to check what the God told you. You see, the God cannot lie. So if you see something during the dream and the God itself came to you and told you the answer, you should probably check the answer.
Okay.
So let's try. So for this, we want to compare phi and phi of H. How do you compare two maps? Two maps are the same if they coincide for all possible elements.
Okay.
So let's compute the left-hand side and the right-hand side and check that they are the same. Okay, by the definition, the right-hand side is just h to the k. Okay?
Okay, it means it's f of 1 to the power k.
Yeah, and this is f of 1 to the power of k.
Why? Ah,
Oh.
okay.
Okay, so okay, let's not skip. I don't want to skip the steps.
Yeah, we have
But
1 plus 1 plus 1 plus
Yeah.
1, but in Arch we have, if we are now within Arch, we have f of 1 multiplied.
But as you can see,
Yeah, they're the same.
they're the same. So that's why every homomorphism has this form.
Okay.
Okay. Well, I'm almost afraid to ask, but are there any other questions?
No, but we have just proved that any homomorphism can be represented in this way. But what about our theorem?
And what again? Yeah, but that's exactly what we wanted. We wanted to describe all possible homomorphisms. We showed that each homomorphism is of this form.
Probably I'm confused with like the amount of information. Could you show, please, our theorem with two implications?
With which one?
Wait,
Okay.
like this one in the second column, in this 10th line. Yeah, this one.
This one. Okay, but this, so I can formulate the same claim for Z. Did I just give me a second? Did I formulate that? Yeah, probably not. That was my mistake. I should have formulated this, well, the claim for Z in a similar way. So, well, if you write Z here, then you don't need this restriction. So what's written here, every element of H gives you a homomorphism from Z to H. You see, just what, let's keep this N
Okay,
here.
but in our previous task, what was K?
Like
we have
there is no K here. There is no K here, just in case. Okay, but that's okay. Let me go back here. So what I described here, I described all homomorphism from Z to H. But now, and let me summarize what happens here. I told you that there is a bijection which takes each element H to a homomorphism phi H. So there is a bijection between all elements from the group H and all the homomorphisms from Z to H. Okay, this is what we proved for the group Z.
Thank you.
But now I'm proving a similar statement, but for the group Zn. So now we want to describe all homomorphisms from Zn to H. How do we describe it? Well, here the final result says that all homomorphisms are in one-to-one correspondence with elements from H with the additional restriction like this. And the rule is exactly the same. H goes to phi of H.
Okay, how to prove this implication?
Okay, we need to do 3 steps as before. The step number 1, the construction. First of all, if we are given an element here such that H to the N is equal to 1, we need to show that this map, which takes K to H to the K, is a homomorphism. Now, well, this is what we need to check. So this is need to check. So how do we check this? Well, we need to check that if we take K1 plus K2 modular N, this is our operation. So K1 operation K2 is actually K1 plus K2 modular N. This is how our operation works. Okay?
What is K?
K is an arbitrary element from Zn.
Okay.
So when
Okay,
I
so
write
we
picture
have,
like, yeah,
we have H small from H, and we want to prove that any K from that n to H to the power N is homomorphism, right?
yeah. So this is the rule this is the rule for the map. So what is the
Okay.
map? The map is a rule which takes element from here and maps to an element from here.
Okay.
When I write this picture, I name the sets for the map above, and I write formula for the elements below. So
Okay.
here K is from here, and where it goes is an element from here.
Okay.
So now I want to show that phi h
But
of,
why do we have K by K equals K plus K modulo 4?
it's a definition of the operation on the remainders. How do you add remainders?
So it's not multiplication, it's our operation, right?
So it's by definition, it's addition modular n.
Okay.
So remainders modular n, so they do not form a group with multiplication. But if you take addition modular n, they form a group.
Okay.
So, and we want to show this property. Where here is this operation, and here is the operation from H.
Okay.
So now, how do you compute K1 plus K2 modular n? You add K1 plus K2 as integers.
Yeah, take a denominator.
Yeah, and then take the remainder. So this
Yeah,
will be R.
Okay.
So by definition, left-hand side goes to H to the R.
Okay.
The right-hand side, this goes to H to the K1. This goes to H to the K2, and then you just multiply them. And now you want to compare these two things. Are they the same? Okay.
Okay.
But you see, here we also know that H to the N is equal to 1, which means that H to the Qn is also equal to 1.
Okay.
Well, but then is H to the R plus Qn is equal to HR times 1 equals HR.
Okay.
But this thing is the same thing as H to the K1 plus K2.
Yeah, okay, it's clear.
And now it's clear, yeah. So because of this restriction, this map is a homomorphism. So if we don't pose this restriction, this map need not be a homomorphism.
Okay.
So now we have some set of homomorphism. Now we want to show that, well, again, for different H, we will get different homomorphisms because, well, they take the element 1 to different elements. So they are all distinct. So the second part, if H is not equal to H prime, then phi of H is not equal to phi of H prime because they take element to H and H prime, respectively.
Is it possible to find different H so that they give the same value?
No, because, okay, let's explain again why. So if we have two different elements, I want to prove that these guys are different. What does it mean that they're different? Well, these guys are maps. When maps are different, when you find a point where these maps give different results, then the maps are different. So let's take a point 1. Then phi of H at 1 will give you H, and phi of H prime at 1 will give you H prime. And since these H and H prime are distinct, the result is different. So this is what I wanted to show here, but in a shorter form.
Okay.
And now we want to show that each homomorphism can be presented in this form. So we want to take an arbitrary homomorphism.
Yeah, but we have already done.
But here there is a subtlety. We haven't done this. We've done this for the group Z. We've done it for the group Z, but here it's for the group Zn. And here we want to prove more. We can find an element H prime from H such that H to the N is equal to 1 and phi is equal to phi of H. So we want to prove more.
Okay.
You see? So this is what we're given, and this is what we want to prove. But we prove this in a similar way, but this is a different thing. And here we want to prove two things. First of all, again, we just take h to be phi of 1, and then we have two things. The thing number one, we want to prove that phi of k is equal to phi h of k for all k from Zn. And the second thing, we want to show that h to the n is equal to 1.
Why do we need it?
Well, because I want to show this, because this construction phi of h works only if h satisfies this restriction.
Okay.
You see, we use this here because if h doesn't satisfy this restriction, it's not a homomorphism. This equality doesn't hold.
Okay.
Okay. So this was a part of our restrictions. We want this to happen. And this will happen. So why this happen? Well, you see, when you take, let's prove B first. When you take 1 plus 1 plus 1 n times, it's equal 0 in Zn.
Okay.
So when you apply phi, you will get this. But now, since phi is a homomorphism, it takes neutral element to the neutral element, which means that this is 1, which is neutral in H.
Okay.
And this goes to phi of 1 to the power of n.
Okay.
So you see, and this is h to the power of n by definition. So we have this restriction.
Okay.
And and when we want to show that this is a that phi of k equals to phi h of k, well, we just compute this by definition. So the right hand, this is done in a similar way. So this is h to the k, and this is phi of 1 plus 1 plus 1 k times. So this is
Okay.
phi of 1 to the k, and yeah, this is by definition exactly the same. So now this completes the proof. Is it okay now?
Yes. Yes. Could you please show the whole blackboard?
Yeah, as you can see, there are a lot of freezes because reasons. Microsoft cannot optimize its whiteboard. Should I zoom in or?
So when we were proving this fact for the set of all integers, we were using phi as h to the power k, right?
Again, when we
were proving this fact for the set of the group of all integers, what was our phi? Phi of k, h to the power k. Okay, it's clear. I had one question about somewhere in the middle,
okay.
about our property, but I don't remember it.
Well, if you remember the question, just write me in the Telegram and I will answer. Or you may come to my consultation hours. That's not a big deal. Do you remember any other questions? Oh, Kirill, I cannot hear you.
Yeah, I'm confused completely. Is everything.
Just in case, do you have any more questions?
For now, I think no.
Okay, then I just hold the recording.